Good day to all of you. I'm very happy that Dr. Mr. Sonbhadra was just now telling me that they have submitted the assignments and they have been doing it very positively. It's that's more important. See, two things which I wanted you people to understand was that problem solving is not from one discipline. It cannot be from one discipline. Entire computer science, entire information technology has got to be involved while solving one single problem, and that's what you would definitely be appreciating, and you are basically good at that. Only thing is that, I mean, I don't need you to remember anything, but I need you to know that the information is available in this source, so you should have the access to that source. That's what an engineer has got to learn. I'm very sure you would have picked up those skills now, because some problems require image processing, some problems might have required matrix algebra, some problems might have required something else like computer graphics. Some problem might have even required a bit of recognition of the shapes, like whether it is a vertex or it is a edge, or some shapes, geometrical shapes. So every problem required more than one field, and essentially you could have now seen that graph theory, the whole idea of graph theory is just an intermediate stage of representing your algorithm, which is the method of solving the problem. And naturally, for the algorithm, you have got to be strong in data structures also. That's what you have enjoyed, and you should continue to enjoy. Now, today, I shall keep my lecture very brief, but I shall get into the diversities of the problems. And I wanted to show that just 2 sessions are enough to cover the entire world problem, entire problems existing in the world. Just 2 sessions are more than enough also. Basically, I did not want to get into specific aspects of data structure, because it is your imagination which has got to come out, and that has got to be assessed. So my assessment, in fact, I have very strictly told Sonbhadra and team, Dr. Javed and team, the assessment is not for the quality of the answer that you produce, but the quality of ability that you display in solving the problem shall be assessed. In fact, I'm not really interested in the end result, but as an engineer, you would go towards getting that end result is more important in the assessment. And that's the reason I don't even believe in final examination, where ultimately, if you are going to reproduce the answer from your memory, that is all. That is not going to solve anything. That is all. That's not going to take you to any end at all. So even if I conduct an examination, it will be to test your ability to handle a crisis. I shall give a problem where it is just a crisis, and you have got to manage to solve a crisis. That's all. And the crisis has got to be solved within the time limit. Therefore, examination will have a time limit like 1 hour or 1.5 hours, not more than that. Okay. But anyhow, let us enjoy all the assessment. That is important. Now, you have seen most important thing till now. You have seen. Can we share the slides now? Can we just quickly run through the? I have just focused mainly upon two things. One is incidence matrix, and another is adjacency matrix. So one is incidence matrix. In incidence matrix, you have the number of rows represent the number of vertices, and number of edges represent the number of columns. Note that we have considered only simple graph till now, and the simple graph, recall the simple graph is the one which shall not have parallel edges, which shall not have self. All right, this is what we have seen, and we have seen that an incidence matrix is rectangular in structure, rectangular in shape. Okay, it will be n cross E matrix, n standing for the number of vertices, E standing for number of edges. It's a simple 0, 1 matrix, a simple binary representation, and the simple binary representation takes it into vector space also. That's the beauty of this. Okay, so there is a column vector, there is a row vector. These are the interesting points in the incidence matrix. Now we have also seen adjacency matrix. Adjacency matrix has got to be represented as X. This is wrong. Dr. Javed has still not updated it. Okay, and the size is also incorrect. It has got to be n cross n matrix, and then n cross n matrix is a square matrix. It is vertices versus vertices. So it is the adjacency matrix. Now these are the two matrices, and based on this, you would have derived various data structure representation. Some of you might have used the matrix itself as a data structure. Some of you might have decided to have different type of data structure evolved from that, probably lists. This is a list of, it's a full matrix as a set of lists. People might have done different ways. I shall try to find out from Sonbhadra. Now we shall continue from here. Now today we are going to get into some diverse issues slowly. All right, I have already handed over 12 problems of assignment to Sonbhadra. He will be distributing those problems. They may be slightly more interesting, but only one interesting point in all of them is they are all dependent upon only these two matrix structures. So you would be constructing the matrix structure and you would be trying to solve a more practical problem. That's all. Okay. All right. We shall go ahead now. So we shall learn a little more formally learn degree relation between n and e. Okay, n is number of vertices, e is number of edges in a graph GNE, and then you count the number of ones in each row. Number of ones in each row, either in incidence matrix or in adjacency matrix, each row. Then that definitely will tell you the number of edges incident on that respective vertex. So the number of edges incident on a respective vertex is called the valency of a vertex or degree of a vertex. It is also called valency of a vertex. It is also called degree of a vertex. Degree of a vertex is more a mathematical terminology. Valency of a vertex, those who still remember chemistry, those who still have inclination towards solving some chemistry problems would definitely understand valency of every vertex is equally important. Okay, so that is why it is called valency of a vertex, degree of a vertex. So let us reproduce figure 1 and figure 2. Figure 1 is a generic graph, has got self loop, has got parallel edges, it also has got an isolated vertex, whereas figure 2 is a simple graph. So you can see that the degree of V1, you can see V1 here, 1, 2, 3, 4 edges. Therefore, degree of V1 is 4. And I am more particular about V4. You look at V4. It has got a self loop. But how many edges are incident on V4? 1, 2, 3, 4. You don't look at the other end. Your vision should be limited only towards the vertex. When you look at the vertex, 2 edges are incident. Therefore, a self loop will be counted twice while the degree is calculated. So degree of V4, 1, 2, 3, 4. All right. So degree of V1 is 4. You can verify this. Now you sum up all these degrees, sigma degrees of all 6 vertices. Incidentally, there is one vertex with 0 degree also. You sum it up and that comes to 16. Total number of edges present in this graph is 8. So I can represent 16 as 2 into 8, which is equal to 2e. So sigma degree is always equal to twice the number of edges. All right. That's a very important starting point in graph theory. What is sigma degree in a graph is equal to 2e. Why? Because each edge contributes to 2 degrees. Right? So one edge contribute 1 degree at this end vertex, another degree at this end vertex. Any edge, if this edge is present, it contributes 1 degree to V5 and edge E7 contributes 1 degree to V3. Therefore, no edges are incident on V6, hence no edge is contributing any degree to the vertex V6. So this is an illustration with a graph, with a simple graph, linear graph. So sigma dvi is equal to twice the number of edges. Now again, before I move over to the next slide, you can see here with reference to figure 1, degree of V1 is 4, which is an even number. Degree of V2 is 3, which is an odd number. Degree of V5 is 1, which is an odd number. So such a vertex is known as odd vertex. This is called an even vertex. Naturally, V6 is also an even vertex because 0 is treated as an even number. So this is an odd vertex. This is an odd vertex. V5 is an odd vertex. V2 is an odd vertex. Remaining are all even vertices with reference to this graph. With reference to this graph, V2 is an odd vertex, V5 is an odd vertex, V1, V3 and V4 are even vertices. Why am I elaborating so much here? You just, out of curiosity, you count the number of odd vertices. Say 1, 2, 3, 4, 5, 6. Out of 6, 2 are odd vertices, V5 and V2. 2 are odd vertices. Let us see here, 1, 2, 3, 4, 5. 5 vertices are there. Out of 5 vertices, 1 and 2. 2 are odd vertices. So there is something very interesting. The total number of odd vertices should always be even in number. That is the next statement which I just wanted to take you. The number of odd degreed vertices in a graph is always even. Let us see. Let us try to give a formal proof. Sigma degree is equal to 2e. 2e is an even number. You know that whatever may be the value of e, 2e becomes an even number. This even number, sigma degree, is distributed as some as odd vertices, some as even vertices. Some of them are odd vertices, some of them are even vertices. So sigma of even vertices should definitely be an even number. Surely this even number is less than this even number 2e. Therefore, if I push it to this side, bigger even number minus smaller even number becomes an even number. So sigma odd will still be an even number. Sigma odd will still be an even number. When can sigma odd be an even number? Only when you add 2 odd numbers, it will become even. Or you add 4 odd numbers, then it will become even. Or you add 6 odd numbers, then it will become even. Therefore, sum of even number of odd numbers can only be even. Hence the proof for this. Okay. All right. Now let's go into some more terminologies. These terminologies would be useful when you start solving the problem. Okay. So if degree of all vertices are same, if degree of V1 is same as degree of V2 is same as degree of V3, etc. The examples are drawn over here. This is a circuit graph. Okay. This is a complete graph. Because let us come to complete graph a little later. But anyhow, now you call it as a complete graph because you cannot insert any more edge into this graph without spoiling the simplicity of this graph. All right. And this is a very interesting graph. If you keep V1, V2, V3 in one set and keep V4, V5, V6 in another set, then you can see the mappings are between the sets, not within the set. See, V1 is not connected to V2 directly. V1 is not connected to V3 directly. Of course, the connectivity is V1, you go to V4, and V4 you can come to V2. That's an indirect connectivity. But what I am trying to tell you is V1, V2, V3 can be considered as vertices in one set, and V4, V5, V6 can be considered as vertices in another set, and all the mapping is between the sets. When I'm telling all the mapping is between the set, in mathematics, all mapping functions y is equal to f of x will belong to this problem. Okay, all mapping problems will belong to this. Okay, when I said that V1, V2, V3 is in one set, V4, V5, V6 is another set, I'm just telling that V1, V2, V3 makes one cluster in a big population. And V4, V5, V6 makes another cluster in a very big population. And we are trying to see how the two clusters are related, not how within the clusters the samples are related. We are trying to see the relationship between the two clusters here. These are the types of problems, okay? In fact, this particular type of graph is known as a bipartite, by two partitions, bipartite graph, and all the mappings are between the partitions. Okay. Now you can again see that this is the maximum mapping possible from V1. V1 can have a relation with V4, V1 can have a relation with V5, V1 can have a relation with V6, and that is the maximum. Okay. Therefore, this type of mapping here is called complete mapping here. So this is complete bipartite mapping, whereas this is complete graph. This is a complete graph, whereas this is neither bipartite nor a complete graph, but a circuit. Is it all right? But a circuit. So here all vertices are of equal degree. All right. So such a graph is called a regular graph. Okay, right. Then we shall look into some more things. So here you saw that V6 degree of V6, valency of V6 is 0. Such a vertex is called isolated vertex. Okay, isolated vertex. Here you can see that the degree of V5 is 1, and such a vertex is called pendant vertex, or it is also called end vertex, or it is also called terminal vertex. Now you can, if you are smart, you would have realized that a graph representation of your algorithm or graph representation of your program straight away tells that if in the graph representation, if there is a vertex which cannot be reached, then there is something problem with that program, with that code. The code does not work. Okay, because in a algorithm, in a code, all vertices should have some connection. If the vertex is like V5, then if that code, in that code, V5 could show the starting point of the algorithm, or V5 could be showing the terminal point of the algorithm, exit point of the algorithm. All right. So these are the interesting points. Like what is then V4? V4 may be a repeated reading structure. It may be a repeated array reading. Okay. So you come back to the same state. It looks like a sort of automata diagram. Okay. So automata diagram is a graph representation. Okay. All right. So a graph n vertices, no edges can be possible. See, this can be possible. Okay. So there are 4 vertices. There are no relationships at all. It can be possible. Okay. Then that is called a null graph. So now you are experiencing that there are huge rain everywhere, whether it is Kerala or Karnataka or Assam. You would only see vertices visible, no edges visible. So it is the null graph. Is it all right? This is the null graph. Similarly, I have not put it here. You may note down. Theoretically, it is possible to think of making n also 0. Theoretically. Then it becomes a 5-5 graph. If it becomes a 5-5 graph, 0-0 gap, then it is called a empty graph. Total space becomes vacuum, empty graph. Okay, so a null graph is one where edges are not present. Empty graph is one where vertices are also not present. Naturally, if I tell vertices are not present, edges are automatically not present, because once if I tell that there is at least one edge, there must be at least 2 vertices, because an edge connects 2 end vertices. If it is a self loop, at least there must be 1 vertex, because the same vertex acts as the end vertices twice. All right. So isolated vertex, pendant vertex, null graph, and empty graph also, which I have not put it here. Okay, it is too early for you to get confused, but still I mentioned that there shall be empty graph, because you will be doing some sort of like your when you start your real life, people would tell that your code is running into 1,000 lines. Can you reduce the code? Can you reduce the number of lines in the code? That could be the general request by your head of the team. So how will you reduce the code? At one stage, when you start reducing, naturally in the process, some vertices will become isolated vertices. That should not happen. And sometimes all of them just become vertices and connectivity could be lost. All right. In the whole process, if reduction is the process, if reduction is the target, ultimately the reduction should end into an empty graph. That vertices also should get removed. Okay. Now, I was just now telling you about the simple complete graph. What is a complete graph? A complete graph is every vertex should be connected to every other vertex, and it should be simple. What do I mean by simple? Because it should not have parallel edges, it should not have self loops. So a simple graph with every vertex connected to every other vertex is called a complete graph. It's called a click. Okay, it's called hotline connection in communication. Okay, in old telephony, we used to call it as a hotline connection. Even without dialing, I should be able to. The moment I pick up my cradle, it definitely dials only your number. So it is a hotline connection. Okay, so it's a click. So if that has got to happen, so in a graph of n vertices, every vertex should be connected to all other n minus 1 vertices. Therefore, degree of every vertex should be n minus 1. Is that clear? Degree of every vertex should be n minus 1, because from one vertex, the connectivity should be established with all the remaining n minus 1 vertices. Therefore, the maximum vertex connectivity or the maximum degree of a vertex cannot exceed n minus 1, because the connectivity is at most with the remaining n minus 1 vertices. Okay. And how many vertices are there? Totally there are n vertices. Therefore, total degree will be n times n minus 1. And you know that sigma degree should always be equal to 2e, twice the number of edges. Just now you have seen the fundamental truth that sigma degree is equal to 2e. So in a complete graph, n into n minus 1 becomes equal to 2e. Therefore, e becomes n into n minus 1 by 2. Therefore, the maximum number of edges in a complete simple graph is n into n minus 1 by 2. In the order notation, it is order of n square by 2. N square, it is order of n square. Therefore, any exhaustive search could be n square. All right. Okay. All right. Let's get into some more interesting things. Finite and infinite graph. GNE. If I tell n and e, it is a finite graph, because n is finite, e is finite. GNE is a finite graph. G, where n starts tending to infinity, e is finite. Definitely is an infinite graph. N starts tending to infinity, e is finite. Therefore, that should imply that it must contain plenty of isolated vertices, isn't it? It must contain lot of isolated vertices. Let us see other type of infinity. N is finite, e tends to infinity. Number of edges would tend to infinity. N is finite. Then all edges should have terminal vertices. You recall that. No edge can be floating in the air without end vertices. Therefore, this would imply that this should contain self loops or should contain parallel edges. Okay. Now G, n tending to infinity, e tending to infinity, may be connected infinite patterns. Where do you come across? Big data, all your big data problems are of this type. N trying to tend to infinity, E trying to tend to infinity. Okay, these are all the big data problems. Okay, right. So now slowly I shall concentrate on this more on matrix representation. They will become the interesting assignments for you. So for everything, you definitely need to go through the matrix as the medium. Matrix will be the starting point for you to define the data structures. Okay. All right. Now let us see. if there are parallel edges. Recall, I very cunningly built up matrix, either incidence matrix or adjacency matrix, only for very simple graph. Okay, no parallel edges, no self loops. Now I am complicating it. Now, the more practical problems. If there are parallel edges, because look at our own campus. If you recollect our campus, then if you can develop it, if you can represent it as a graph, then you might have seen that there are many parallel edges between two sets of vertices. All right, parallel edges. Which matrix representation can handle parallel edges? Think a bit. So incidence matrix can comfortably handle parallel edges because every column indicates one edge. So if it is a parallel edge, insert one more column. That is all. The job is done. All right, the job is done. All that you have got to do is increase the number of columns to accommodate parallel edges. But how will you do it in adjacency matrix? That is the question. How will you do it? So if there are parallel edges, how will you accommodate? How will you represent your adjacency matrix? Here starts your assignment. You have got to start thinking. Maybe some books, say maybe some Google will give some suggestion, but your suggestion, you take the inputs from all those suggestions, but you can make a better suggestion how to handle the parallel edges, how to represent. First, come out with the problem of how to represent the parallel edges, and incidentally, incidence matrix automatically takes care of parallel edges, but adjacency matrix cannot take care of parallel edges. So how? That is the question. Okay, I'm not going to give the answer because I don't want you to think the way I think. You should think differently so that I can learn from you. All right. So now the next question is self loops. Which matrix representation can handle self loops? Note here, when you count the number of ones in every row, either in incidence matrix or in adjacency matrix, it should represent the degree of that vertex. All right. So now how do you represent self loop? And you know that self loop contributes to a degree of 2 on a particular vertex, which you are just now seeing. So you have got to keep all these things in your mind when you modify the matrix representation. So in the adjacency matrix, recall in the adjacency matrix, X, the diagonal part is connectivity from V1 to V1. Diagonal part is connectivity from V2 to V2. So the diagonal element can represent a connectivity from Vi to Vi, but just entering a 1 there will not solve the problem. If you just enter 1 and count the total number of ones either in the row or in the column, will not become degree of the vertex. Therefore, you may have to enter it as 2. In the diagonal, you have got to enter a number as 2. But once you enter a number 2, the beauty of the matrix as a binary matrix is lost. It is no more a binary matrix. Therefore, recall the problem of coding the matrix like a binary code will vanish. However, you may have to go for one more symbol called 2. One symbol is 0, one symbol is 1, another symbol is now 2 if you want to take care of self loop. But there is a provision automatically available in an adjacency matrix to represent a self loop, but the same provision is not available in incidence matrix. Is it okay? So under the circumstances, I still want to represent it as an incidence matrix. How will you modify? What sacrifice you have got to do? However, how generality can be still reflected in that incidence matrix, how all those properties like counting the number of ones in every row, total count sigma of every row gives this, and how in a column only 2 ones should be present in a column, particularly with reference to incidence matrix, which can make it a column vector, which can definitely provide an automatic validation when a matrix is constructed automatically by an image or by a picture or whatever. All these things have got to be looked into. So remember now, parallel edges, self loops are going to be the problem. Purposefully, I did not teach these things in the first class because I did not want to make your life uncomfortable. Now that life is not uncomfortable, the life is challenging, and you have to take up this challenge and solve it. Okay, and only one batch will solve it, and all other batches will enjoy the fruit of how they have solved it. Okay, all right. So parallel edges and self loops. Now, given a matrix, somehow I have constructed a matrix. Let us assume I have constructed a matrix where parallel edges are present, where self loops are present. Now my question is, I have given you a matrix. How will you detect the isolated vertices in the matrix? How will you detect the pendant vertices? How will you detect the pendant edges? How will you tell which is the first neighbor of some particular vertex Vi? Which is the second neighbor of some particular vertex Vi? All right. So who is the first neighbor of Vi? Who is the second neighbor of Vi? So this is the starting point of your entire pattern recognition language. In pattern recognition, you are going to speak about k nearest neighbors. But now I am just talking to you, and just I am introducing you to telling that every vertex is immediately connected to some other vertex. Immediate connectivity is visible, and that is called the strongest friendship. If I look at you and if I tell who is your friend immediately, then that friend has got to be strong connected to you, or he must be your first neighbor. Is it all right? And similarly, there can be a second neighbor. A friend of your friend is also your friend. Then, however, he is not a direct friend. Therefore, he is second connected neighbor. So, can it be possible to visualize either from A matrix or from X matrix the first neighbor connectivity of every vertex, second neighbor connectivity of every vertex? Is that okay? That is what is the connectivity problem. We take up connectivity in greater detail in the next set of lectures, but right now you should be able to see whether V2 is connected to V5 directly or not, whether V2 is connected to V6 via V3, and V3 is the first neighbor of V1. Such things, such small, simple things, you should be able to do that. You should also be able to do detecting the presence of parallel edges. Okay, I think, have I listed it? Let me see. Have I listed that? Okay, okay, all right. If Vi and Vj are connected, okay, would it mean that there is a path between Vi and Vj? Is there only one path between Vi and Vj? Or will there be more than one path between Vi and Vj? How many connectivities are possible between Vi and Vj? All right. And if there are more than one connectivity possible between Vi and Vj, what is the minimum connectivity? The minimum connectivity is a minimum path length. Okay, minimum path length. Okay, right. So this is another interesting problem. Now, another problem is if somehow I have got an incidence matrix, let us say, and now you know that in incidence matrix automatically parallel edges can be taken care of. Can you detect all parallel edges automatically? Parallel edge need not be one pair. It can be more than one parallel edge to a given edge. It can be 3 parallel edges. It can be 4 parallel edges. Okay, I have just given you the matrix. Find out all the parallel edges and remove all the parallel edges. Represent all parallel edges by one edge is the question. Okay, and then tell how many parallel edges are there. give a linked data structure and tell that how many parallel edges are there. That is also a method of reducing the size of the matrix. Okay, so how will you automatically recognize all parallel edges? All parallel edges, not edges which are parallel to one particular edges. All edges which are parallel to every edge. Okay, all different combinations. How do you find out? Okay, it's not a very easy problem. It is going to be an exhaustive search problem. Okay, and find out what is the complexity of your scanning. How many times you have got to scan the matrix? Okay, so if I take the first edge, to find out all edges which can be parallel to the first edge, might be one scanning. After scanning, how will you reduce the size of the matrix? And then take the second valid edge. Then reduce the size of the matrix. Then reduce the size of the matrix. Can you now see that there is a way towards the end, matrix will become null. It will not become empty because edges are empty. Okay, vertices still remain. Okay, but if there is a way of removing the rows also for some other reason, then you can see the matrix becomes rowless or n becomes 0. When n becomes 0, it becomes an empty matrix. Is that okay? That is the termination of the algorithm. Okay, all right. Now let me go to a little more interesting problem. Just starting from Vi, I want to construct a circuit. What is a circuit? Circuit is just tracing through all the connectivity in such a way that I come back to Vi. Okay, I come back to Vi. So just trace a circuit. You are not given a diagram now. If the diagram is given, vision works. That is the vision algorithm. Now, the same vision algorithm has got to be built on a matrix representation or on a data structure representation. The traversal is made in the data structure, and you should indicate that this is the circuit as if you would recognize the presence of a circuit in a geometrical representation, in a graphics representation, or in a diagrammic representation. Did you get that? So starting from Vi, can it be possible to trace a circuit? Okay, so that can be the problem. Okay, I have already given 12 problems. I do not know which are the problems which I have given. Now, little more interesting, one step ahead now. If till now I have not given the directions with the pair of vertices or edge, every edge did not contain any specific direction. Of course, the absence of marking the direction implies that you can move from Vi to Vj, and you can also move from Vj to Vi. So it is not directionless, but it is bidirectional. It is bidirectional. Okay, you can move in this as well. You can move here. So in fact, in our campus, all roads are bidirectional. You can move in both the directions. Whereas in a big city like Calcutta, like Bombay, like in Bangalore or Delhi, you can see that certain roads are one ways. You can move only from Vi to Vj. You cannot move from Vj to Vi. So it is unidirectional. Is it all right? So if you know electronics, diode is unidirectional. Okay, your transistor is unidirectional. It is not bidirectional. Whereas a resistor is bidirectional, isn't it? So it is a undirected graph is bidirectional. Whereas now if I put the direction, then it becomes a directed graph. Then it becomes a digraph, directional graph or digraph. And now the question is, how will you modify your incidence matrix to show this direction also? How will you modify your adjacency matrix to show, to contain this sense of direction also? All right. Can you still work with only two symbols, 0 and 1? May not be possible now. You have got to raise the number of symbols. If you raise the number of symbols, the binary nature of the matrix is lost. Data structure becomes little more complex. Nevertheless, it is necessary because directions have got to be inserted. Directions have got to be included. Okay. So in a diagram, how will you modify? How edges will definitely have directions. How will you modify the matrix? Okay. So if matrix representation, then there shall be, you consider any vertex, there shall be some edges coming into the vertex, some edges going out of the vertex. Therefore now degree of a vertex will be decomposed into degree in and degree out also. Degree in and degree out. And now degree in overall sigma degree in should be equal to sigma degree out, and that should be equal to E. You prove it by yourself. Okay. So how to trace the directed paths now? How to trace the directed circuits? How to obtain all directed paths from Vi to Vj? How basically to represent this diagram? All right. By the way, if you come back, if your teachers have already told that N-Dev is one very good textbook, of course, of late nobody has written such a quality book on graph theory, but N-Dev doesn't give the algorithms like I am speaking. Yet when if you were to follow N-Dev, you need not follow any book. Just my lectures and Google material is more than enough, and you start solving the problem, that is more than enough. But in case you happen to see N-Dev, you can see that I am through chapter number 1, and now I have already jumped into another chapter called digraphs, which is almost at the second part of the book. And then I have also covered vector spaces. I have also covered matrix representation. You should be seeing that. So I am not going in one specific sequence. You just follow my sequence. Okay. All right. Okay. Now this is another. If a matrix is not connected, I will come to this more. I come to deal this more in the next class. If the matrix is not connected, if it has got connected sub components like G1 is connected, G2 is connected, G3 is connected, and in total G, then will there be matrix representation? Will it have some different representations? Well, maybe I shall speak about it in the next class only, but you need not worry here. But then the matrix has a beautiful representation then. Okay. All right. So now let me come to more interesting problems. I have considered only English alphabets for illustration, English uppercase alphabets only for illustration. You can take up any example for that matter, anything you like. All right. And I might be focusing more towards OCR like application. You may consider anything like road signals, like the language representation for blind, language representation for deaf and dumb. You can consider all those symbolic signal representations. See here, this is X, right? How many vertices are there? One pendant, another pendant, another pendant, another pendant. 4 pendant vertices are there. And look at one vertex, and the degree of this vertex is 4 maximum. All right. Look at K also. Look at K also. K also has one vertex, which is 4 vertex. Degree is 4. K also has 1, 2, 3, 4 pendant vertices. So when you go for general matrix representation, either incidence matrix or adjacency matrix as the knowledge base to represent X or K, both are identical matrices. How will you make out that this is X or this is K? So I want to represent I want to write a OCR. How can my OCR recognize the difference between X or K if I employ incidence matrix or if I employ adjacency matrix? What should I do? So what modification should I do in matrix representation? I will just give you some clue, but I want to know more clues from you. Okay, you can see that this is a line going in northeast direction, isn't it? Northeast direction. Whereas this is a line going in the northwest direction. This edge is northeast, this edge is northwest, and this edge is southeast. This edge is southwest. Whereas in K, one is going north, another is going south, only one edge is going northeast, another edge is going southeast. Can I represent this? Northeast, northwest, southeast, southwest, north, south, east, west. Also, while describing the edges in the incidence matrix, in the adjacency matrix, then I can resolve the problem of X and K. I can definitely resolve the problem of X and K. Is it okay? Can you do that? So that is my question. My question is, now if I have got some geometric representation, all these are geometric representation. That is why they are all called graphemes. Graphemes are the way you write. Okay, graphic representation of writing. Okay, how will you represent the difference? How will the OCR work? Can the OCR work through your incidence matrix or your adjacency matrix representation? So how will you modify that? So did you get that? I told that the 9 directions, 9. So can I have this direction? Northeast, southeast. This is north, this is south. Whereas here, northeast, southeast, northwest, southwest. No north, no east, no west. So that's what is the difference. But how to include this as a code along with your 0, 1, along with or modify the matrix? Imagination is yours. Do whatever. Okay. So this time assignments will be more to test your imagination ability, and naturally how your imagination would become advanced data representation and advanced data structures. That is all is my problem. Now you look at this problem, T. You just look at T. T has how many edges? 1, 2, 3. Even Y has 3 edges. 1, 2, 3. Right? How is the difference? What is the difference? Can you incorporate the sense of direction also? So luckily I have chosen all these with the straight line edges, isn't it? They're all straight line edges in these examples. Okay. Well, you just now work with straight line edges. That is more than enough. Next problem, or some other group may get non-straight line edges. Okay. So design to recognize the input pattern. Now come, you are designing the matrix. You are designing a data structure. Right? Now, second level, you design with the standard, the data set with the standard representation. Okay, that let us call it as making the machine to learn, making the machine to understand that X has northeast edge, northwest edge, southeast edge, and southwest edge, and from where the edge is counted, you give some label to this and tell from this vertex position all the northeast, northwest, southeast, southwest directions are possible. You can tell that, and you can additionally describe there shall be 4 pendant edges, therefore there are 4 pendant vertices, and there is only one vertex which is of degree 4, and all the remaining are of degree 1, etc., etc., etc. This is the training of learning, and this we shall call it as, in pattern recognition, we just call it as training stage, learning stage. I want you to make the machine learn with some standard shapes like this, very standard shapes like this. Okay? But if it is handwritten, using that knowledge, using the knowledge that you have learned from standard shapes, can you tell that this is a X hand drawn, this is a Y hand drawn, this is a T hand drawn? Can you tell that? That is the recognition. That is all these great people who tell that they are doing very big work in pattern recognition do only this thing. One is machine learning and making the machine to recognize. Machine learning and machine recognition. Okay, and that has become a great industry today, machine learning and advanced learning. Okay, so please take it up. Okay, that's a very interesting problem. But right now, don't make the whole world to be solved now. You take up only selected set of samples. Like I've told, X and K is one set of samples. Y and L. You just write a very special OCR to decipher Y from L, L from Y. That is all. Okay. Define a very simple and define a simple graph manipulation language only for this purpose. Take a very subset of a problem. Then you will become an expert. And your expertise, once you may start thinking of designing graph manipulation language. And these graph manipulation languages are basically C inspired, or they can all be C code, or they can all be C functions or C++ functions, or they can be Python functions. Somebody, if you are very interested and talented, you may tell that I will do it in Lisp coding or Prolog coding, do whatever. But then note here, what is really going to happen is you are also inventing a language to solve the problem, and that language are the functions that you are developing, and that becomes the GML, graph manipulation language. Okay, so if you are interested in creating the language, your flow, your research channelizes into developing the languages for some particular purposes, and to avoid writing the compiler, you make them completely C function, because basic compiler is C compiler, it starts working. All right, or it is Python compiler, it starts working, make all of them Python functions only. All right, you do that, or you write your own language. And if you are, some of you could be very much interested in writing a compiler also for your language, do that. That is what is the inspiration from graph theory. Do that. And that should become your project work. That should become your MTech work. That should become your research work later. That's what we are going to do it. Okay. And that's what industry is going to expect also. Okay. Solve some live problems. Is it all right? But in the assignment, I am not asking you to write an entire OCR for an entire English script for handwritten. That becomes a very big research problem. But right now, you start that beginning, like how to write a compiler to recognize X and K, X from K, and then try to include all of them. Try to include all of them. Okay, some of them may be 3 vertex problems, some of them may be 4 vertex problems, some of them may be 2 vertex problems. Solve, start solving. Okay, all right. Okay, so now I shall take a little more interesting problems. How if edge weights, what is the edge weight? The weight given to the edge, some number, description, some description given to the edge. Okay, if edge weight is available, how to incorporate it in the matrix representation? What can be the edge weight? Length of the road can be the edge weight. What can be the edge weight? Some of you know that if I go on this road, if I take this road, there shall be 5 traffic lights in this road. 5 traffic light is the weight of that edge, not the length of the road. 5 traffic lights present in the road is the weight of the edge. Okay, some of you might be working on the width of the road as the edge weight. Is it all right? So 1. If every edge has got 1 weight, 1 number, 1 value associated with every edge, how will you modify the matrix representation? It could be incidence, it could be adjacency matrix. Okay, so the cost of the edge, how will you include the cost of the edge? You are an engineer, you should not stop at that stage. You should now start thinking every edge can have multiple weights. Is it all right? For example, length of the road, distance of the road, number of traffic lights available, width of the road, and width of the road could vary along the edge itself. Along one road length itself, width of the road could be varying. For example, at the outskirts of Delhi, the width of the road will be very, very big, very wide. Whereas after the outskirts, suddenly 6 lane can get reduced to 4 lane, and somewhere it could get reduced to 2 lane. How will you represent this? In the matrix represented, they have the graph representation, right? Okay, and then see how this problem leads to another way. What is the time taken by your car if you drive on such a road which has got 6 lanes in the beginning, 4 lanes later, and will become 2 lanes, and the amount of traffic is so much? These are all edge weights. How will you manage this? Is it okay? All right. So, for simple problem, if the weights of the edges are given, how will you modify the matrix? It is your idea. You can consult any book, you can consult Google, you can discuss with any person, but you justify it, put it, and then when you write your paper, you also tell the idea was borrowed from here, the idea has been taken from here. Don't plagiarize. Don't plagiarize, right? So you just tell that, acknowledge it, and tell it, and also tell why did you think that was the best way that could be done, and therefore there was no other additional thinking to be done by me in that by our batch. Now here, how vertex weights could be considered in a graph? Can you consider the vertex weight? Yes, we should be able to consider the vertex weight. For example, some of you must have already started using neural networks. In neural network, you can see that not only edges have got the weights, even the vertices have got the weights, isn't it? I will give you a very simple example. When a train is moving, it definitely moves on a edge. And when it is moving on an edge, the speed on the edge is one parameter, which is a weight. But in the railway station, it has got to halt. When it halts in a railway station, the time duration it takes to halt, the stop period given to the train in the railway station is the vertex weight. This train halts for 5 minutes. This train halts for 4 minutes. So that's a vertex weight. Is it all right? So even in our body, there are very important vertices. If heart is considered as a vertex, that heart itself internally is made up of 4 vertices, and all these 4 vertices are connected by notional edges because the blood moves over there. All right. How long blood will stay in each chamber is the vertex weight. Is it all right? Is the vertex weight. So how will you modify the matrix representation when vertex weights are also given, when edge weights are also given? Okay. So give that. Now I give some more interesting problems. See here, inclination of edges only will make the difference between M and W. Is it all right? So if you just consider a matrix, simple matrix representation of what is that matrix? Adjacency matrix or incidence matrix. Both M and W will have the same. And how will you include this inclination? Or probably something like the edge length also. This is a shorter length, this is a longer length. Can I include that? In fact, next I have told you lengths of the edges, long and short edges. See here, this is a short edge, this is a long edge, this is a long edge, and while writing lambda, this is fairly medium edge, and a small edge. Okay, here all 3 are medium edges. Can I introduce this? The relative lengths of edges also as weights, So inclination as a weight, direction as a weight, and length of the edges as weights can be modify our matrices. That's the interesting problem for you next time. So I'm really taking you, depending upon your interest, either to develop a graph manipulation language or inventors of your data structures, or or inventors of your imagination pointers, or if you are going to invent your gap manipulation language, then I am going to take you to construct the compilers also. It depends upon your interest and how you channelize yourself. Now let us come to these interesting problems. Here, slightly more complicated. Edges are not straight line edges. They have become curves. All right? Okay. Non-linear edges. They have become curves. All right? So, can you somehow introduce in the matrix that this edge is curvy? This edge is straight line. Linear and a non-linear edge. If it is non-linear, you should be able to tell me whether it is convex or concave or whatever it is. Because ultimately, my point is recognition of the object. How do I differentiate between yes and 5, yes and 5, 6 and 9 for that matter? How will you differentiate? So it is a flipped version. 6 is flipped and rotated version, 6 and 9. All right? Okay, so can you do this? I mean, there's no question of can you do it. You have got to do it. You have enough time, but obviously your imagination. Okay, so these are the problem. Now I have been more towards OCR because my field of interest was document image analysis. Now I am not doing anything except busy over nothing, being an administrator. But then this was my historic interest. Therefore, I want my children to take up this and make me learn more tricks, make me learn more skills because of your skills. All right? Okay, this is what I want you to do. So that is enough for the day. These are the types of assignments. Okay, and these assignments are more interesting. Starting point is just the construction of the matrix. You construct the matrices, either adjacency or incidence or both. All right, and the construction of the matrix, you do it manually, you do it human interaction. So make the machine learn by human interaction. So it is a HCI, human computer interaction. Let the learning be human guided, but let the recognition be by the machine. Later, within the next 10 days, if it is possible, can you also make learning automatic? Like take a photograph, automatically learn from it. Or take an image, automatically learn from that. Like some of your classmates have already done that. So take that software from them, collect that, and use that software to see whether even learning by the machine could be made automatic. But my point is, I don't want you to make the learning exhaustive. I don't want different varieties of samples of X being taken by you and machine should learn about all those varieties of X. I don't want that. I want X to be learned by one machine printed, okay, standard font size, standard font style, only to understand the shape of X. And how should the machine understand the shape of X? Through the incidence matrix representation, or through adjacency matrix representation, or by the combination of both of them. But 0, 1 is not enough. That is the whole attempt in my today's class. 0, 1 coding is not just enough. 2 symbols are not enough. You have got to use more symbols. All right. How will you do that? How will you manage that? And how will the machine learn? Through HCI, human computer interaction. Then once that becomes the knowledge, how can I use that knowledge to recognize any character, to recognize any X, either written by you or written by your friend or written by me or even machine written in a different font style. Is it okay? All right. So I have chosen very selective 12 problems which Mr. Sonbhadra will be distributing today, and that should be more than enough. And now I will stop sharing the screen. I just want to come back to see you people and discuss, take up some